Okay, and we reach our final video in two-stage Simplex. This is a three-dimensional minimization problem. Because it's 3D, we cannot have a graphical solution to this, or at least not one I'm going to draw on paper for you. And it's a minimization problem, so we'll just look at briefly how that affects our procedures. And it is two-stage Simplex. Okay, so a question of my own design. A manufacturer produces packets of crisps using three different cooking methods. We've got air frying, baking, and oil frying. Each day, the manufacturer has enough potatoes to make either 800 packets of air-fried crisps, 1,000 packets of baked crisps, or 1,200 packets of oil-fried crisps. And each day, the manufacturer is required to produce exactly 1,000 packets of crisps. So we could, in theory, use that constraint to bring it down to a two-dimensional problem and solve it graphically. That is an option there, but I'm not going to do that in this video. Each day the manufacturer is required to produce at least 200 packets of baked crisps, and each day the manufacturer is required to produce at least 300 packets of oil-fried crisps. There is a cost to produce a packet of crisps, which depends on the method of cooking. A packet of air-fried crisps costs 10 pence, baked costs 20, and oil-fried costs 15. By defining appropriate variables, solve this linear programming problem to minimize the daily production cost of the above constraints. Okay. So, we do need to be able to extract a linear program from text. That is part of the course. I have done a video on this already, and I've designed this question to hit some particular constraints which come up, and you need to know how to deal with those. Okay, so first of all, we need to define our variables. So when you need to define variables, i.e. they're not given to you in the question, we must make sure that they are clearly defined. So I'm going to say let. Now, my three variables are the number of air-fried packets of crisps made, baked, and then oil-fried. So they've got three variables there. So I'm going to just write a vector. So I'm going to say let A, B, and let's call it F, just because O looks like a 0. So I've got air-fried, baked, and oil-fried. B, the number of packets of, and then my vector here, air-fried, baked, and oil-fried crisps produced. Okay, the key part here is I've used the phrase be the number of. Whenever you're asked to define variables, you should use that little phraseology there, be the number of. Don't just say let A be air-fried crisps. Okay, that doesn't make sense. Okay, let A be the number of packets of air-fried crisps produced. Okay. Okay. Now we've defined those variables, we can produce a linear program. So we want to minimize the daily production cost. Okay, so minimize the daily production cost. So I'm going to minimize, I'm still going to call it P, but I guess you could call it C here for cost. So I'm going to minimize 10A, 10A, because it costs 10 pence to produce a pack of air-fried crisps, plus 20B, and then plus 15F. Okay, so there's my objective. And then subject to. And now I'm going to write these constraints. Now each bullet point above is going to be a constraint. So each day the manufacturer has enough potatoes to make either 800 packets of air-fried crisps, 1,000 packets of baked crisps, or 1,200 packets of oil-fried crisps. I've tackled this kind of constraint in a previous video when I did graphical linear programming, but let's just recap here. Let's say I produced 800 packets of air-fried crisps. That means I could produce nothing of either of the others. So, because I've used all my potatoes on that. So if I were to do that, then A over 800 would be the number 1. Okay, that's the maximum it could be. But if I produced only 400 packets of air-fried crisps, that's used half the potatoes, which means I could then produce either 500 baked crisps, packets of baked crisps, or 600 packets of oil-fried crisps. So it's some kind of linear relationship between these. But the best way to do it is to do it as I'm doing it here. So A over 800. And then I could argue the same thing for the other two as well. So by symmetry, I'm going to end up with plus B over 1000 and then plus C over 1200. And that must be less than or equal to the number 1. So that if C, for example, was 1200, that would force A and B to be 0. And I couldn't produce any of those. However, if C was 600, then I still have half my potatoes left, which I could distribute across A and B. Essentially, what each of these fractions represents the proportion of potatoes I'm using on that cooking method. Okay, so that's the first constraint, and that's the first bullet point. Okay, the second one. Each day, the manufacturer is required to produce exactly 1,000 packets of crisps. So that means I'm going to have A plus B plus F. That's the total of all my packets of crisps. And that needs to be equal to 1,000. That is not an inequality constraint, it is an equality constraint. And as I mentioned earlier, that could be used to bring the problem down to a two-dimensional one to solve graphically. But we're not going to do that here. Third bullet point, each day the manufacturer is required to produce at least 200 packets of baked crisps. So we require the number of baked crisps, which I've defined as being B, must be greater than or equal to 200. And then the bottom constraint is very similar. Each day the manufacturer is required to produce at least 300 packets of oil-fried crisps. And again, look at my definitions. F is my definition of oil-fried crisps, packets of oil-fried crisps produced, and that must be greater than or equal to 300. Right, so those are my 4 constraints. 1, 2, 3, 4. Each comes from a bullet point, and then I've got my objective function as well. Okay, so that is the linear program. Now I need to get it set up for Simplex. So for Simplex, this is the objective. So I'm just going to whack everything across to the other side. So that's no problems over there. This one here, I'm just going to pop in a slack variable and then change it to an equal sign. And then these 3 constraints are a little bit different because none of them contain the origin. So all 3 of these are going to give me an artificial variable. And then also, I've chosen this constraint for a very particular purpose because I want to show you what you do with an equality constraint in two-stage Simplex, or in Simplex in general. So let's have a look at this constraint here. What I'm actually going to do is I'm going to take this constraint, A plus B plus F, and split it up into 2 constraints, which both contain inequalities. So I'm going to say A plus B plus F must be at least 1,000, but I'm also going to say that A plus B plus F cannot exceed 1,000. So those 2 constraints together actually form this constraint. And that's how we deal with an equality constraint when we are dealing with Simplex. And then we can deal with these 2 constraints separately, just as we would normally with Simplex. So this bottom one is good to go because the origin is satisfied. So that just becomes A plus B plus F plus a slack equals 1,000. And then this one, the origin does not satisfy, so that's going to give me an artificial and a surplus variable. So I'm going to get A plus B plus F subtract a surplus plus an artificial, and that's going to equal 1,000. And that can be seen in my previous video. Okay, and then these 2 constraints, again, the origin does not satisfy, so I need to introduce a surplus and an artificial. So I get B subtract a surplus plus an artificial is equal to 200, and then I'm going to get F subtract a surplus plus an artificial, and that's going to be equal to 300. Okay, so we take all of that information and we stick that into our initial tableau. Okay. So here's my initial tableau, really big tableau. So we get 0, 1, then the objective was 10A plus 20B plus 15F. So I'm going to get 10A plus 20B plus 15F. There were no other constraints, and the right hand side is initially 0 because we're starting at the origin. Okay. And then I'll come back to the top row at the end. Then I've got these constraints. So I've got this potato constraint, So that is 1 over 800, so A over 800 plus B over 1000 plus C over 1200 plus a slack, and that's going to be equal to the number 1. Everything else in that row is 0. Okay, so that was this potato constraint. Then we've also got this constraint here, which was one from the equality constraint, but this one doesn't contain any surplus or artificial variables. So I'm going to put this one in next. So it's 1a plus 1b plus 1f plus a second slack. So 1a, 1b, 1f, and a second slack, and that came to 1000. Zeros everywhere else. And then its partner, this one here, I might as well put that one in next to it, was the other half of this equality constraint. And that's, instead of the plus S2, it's got a minus S1 plus A1. So I'm going to pop that one in next. And it still equals 1000. Okay, then we've got our 2 constraints from the bottom. So we need at least 200 packets of baked and 300 packets of oil fried. So baked, 1 baked, a surplus, which is S4, another artificial, which is A2, and that was 200, needs at least 200 packets of baked crisps. And then this one at the bottom here, need at least 300 packets of oil fried crisps. It looks like that. And now that I've got those 3, what I can do is I can say, well, this top row here is going to be the sum of these 3 rows. And it's these 3 rows because those are the 3 rows that contain artificials. So the artificial variables come to the top, 1, 1, 1, but I'm going to replace that 1, 1, 1 with a 1 over here because capital A is defined as A1 plus A2 plus A3. Now I just need to add the others. So 1 plus 0 is 1, 1 plus 1 plus 0 is 2, 1 plus 0 plus 1 is 2, and 0 plus 0 plus 0 is 0. And then I'm going to get 0 there, a 0 there, a minus 1 there, minus 1 there, minus 1 there, and I'm going to get 500 there. Okay. Oh no, I'm not going to get 1,500 there. Okay. So that is my initial tableau. And that is all you really are going to be asked to do in an exam. You would not be asked to carry out an iteration of this. This table is too big. It's going to take too much time for the examination. But they could ask you to describe where you would go from there. So our first objective is to minimize this top row. That will eventually bring A to 0, which means you're then in the feasible region. And then you can move about the feasible region by maximizing the second row. Minimizing the second row, sorry, because it's a minimization problem, to get us to our optimal vertex. So I'm not going to do any iterations for this video, but what I am going to do is I'm going to conduct a ratio test. So first of all, I'm just going to choose column F, just because I've got that highlighted here in my notes, and then conduct a ratio test. So 1 divided by 1 over 1200 is 1200. 1000 divided by 1 is 1000. 1000 divided by 1 is 1000. 200 divided by 0, that's, we'll call it infinite. And then 300 divided by 1 is 300. So that's the smallest positive value from our ratio test. So therefore that is the column that's chosen. Therefore that is our first pivot. Okay. So what I've got here is I'm going to show you my notes. That is our initial tableau. We can see our ratio test values, which we've just calculated, 1200, 1000, 1000, Excel error, and then the 300, which is the one I've selected. And if I pivot about that point, I end up at the next tableau. If you want a challenge, take that tableau and run it through. There are slightly different routes you can take. For example, I could have chosen column B first rather than column F. So your results may end up being slightly different than mine. Let's just roll through the solutions here. So if you chose column F, this will be your first tableau, the first iteration. Then conducting a ratio test again. There's no choice there. I've got to choose B because that's the only one with a positive 2 in that row. So conduct a ratio test, you will end up with that one, which then leads us to this tableau. And then again, you've got a choice at this point, S4 or S5, because they're both positive 1. Or or A actually, chose that as well. I chose S4, which then led us to that. And again, I could have chosen which one of those to go to as well. Also notice here there's a negative value from our ratio test. We ignore those. Okay, so don't choose a negative value from a ratio test. That led us on to this tableau, where finally we've gone from an A value of 500 to an A value of 0. So because A is now 0, that means that we are, oh, actually, no, we're not quite. It's not quite, well, we are in the feasible region because A is 0. However, A1 is 0 by basic variable, not by column of junk. So actually, although we are in the feasible region, Simplex doesn't think we are yet. We actually need to do one further iteration to think we are. This one says that we are in the feasible region because we've got capital A equals A1 plus A2 plus A3. Okay, that's what that top equation states. Yeah, it's kind of a situation where you have multiple constraints meeting at a single point. We are at that point graphically, but it's not quite twigged yet from here that we are in the feasible region from Simplex's point of view. Okay, we end up here. So now we are in the feasible region. We can just ignore the top columns and we can actually delete those 3 columns as well. Top row gone, those 2 columns gone. And we can just carry on as normal. And we end up with these 2 tableaus. And then finally we end up here. This is our optimal solution because P is now minimized. But notice that P is negative. Okay, it's an interesting point that P is negative. And that's just because of the way P was defined. Why is it negative?